So up to the first 10 electrons that we put on atoms, we now know the shapes those electrons will take. What are their orbitals? Which ones are higher in energy? Which ones are lower? That is what quantum numbers is telling us. Well, the periodic table is set up to represent these. 1, 2, 3, 4. The periods of the periodic table, the rows, are tied to the n values. Notice in the first row, there's only 2 elements, hydrogen and helium. Hydrogen has 1 electron, helium has 2. They are put in that row because they are all the things in the n equals 1. The second row, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, you'll notice there are 8 elements in it. So 1, 2, 3, 4, 5, 6, 7, 8. And you'll notice how many electrons did we put in the n equals 2's? We put 8. That second row is all the things that have their last electron go into an n equals 2. Lithium and beryllium, you'll notice, are on this far left columns. These are the s orbitals. Everything in those columns will have the last electron go into an s orbital. So this one would have been lithium, this one would have been beryllium. The 5th electron, well, that was boron, is the 5th element in the periodic table. This whole section over on the right, the 6 elements in that section, and you'll notice there are 6 electrons to fill the p orbitals. This is the p block. The periodic table is actually broken up to represent those orbitals. So where something falls on the periodic table tells you about the orbitals and which ones are full and which ones aren't. If we were to pick something at random, sulfur, well, it is in the 3rd row, so it's going to be n of 3, and it's in the p block, so its last electron is going to be in the p's. Because it's the 1, 2, 3, 4th element into the p's, it's going to be 4 electrons in the p's. If you tried to solve for sulfur, sulfur has 16 total electrons. Well, 1s, 2s, 1, 2, 3, 4, 2 p's, 5, 6, 7, 8, 9, 10. I'm out of things that only have 1 node. I have to bump up the things that have 2 nodes. So I need n equals 3 now. What are all the things that have 2 nodes? Well, I can have a 3s. I can have 3p, and you can even get 3ds. What are my options when I have 3 nodes? Well, remember, my L's can be 0 through n minus 1, so 0, 1, and 2. L's are planar nodes. Here's 1 planar node, here's 2 planar nodes. I can get SP's and D's. And so I have those 3 available. They are possible shapes once I'm using things that have 2 nodes. Which one's lowest in energy? Radial nodes are lower than planar nodes. And so 3s is going to be lower than 3p. 1 planar node is less than 2 planar nodes, so 3p will be below 3d. If we keep filling electrons, I was up to 10. Here's 11, 12, 13, 14, 15. 16 electrons have been added, which is what we said sulfur had, being the 16th element. And it filled 4 of them into the 3p. Go back and look. Well, it was in the 3rd row, so it was n equals 3. It was in the p block, and it was the 4th element in the p block. Just by looking at where sulfur is, we could have determined that its last electron was the fourth to go into the 3p's. The periodic table is set up to actually let us find this info very quickly. As an aside, what does the 3s look like? Well, it's s, so it has no planar nodes. But n is 3, so it must have 2 total nodes. So I can't have a planar node. My only option is to have a radial. But that change, that's 1 node. So I have to have a second change. A 3s orbital looks like that. Plus, then minus, then plus. The outside edge is not another node. It's just we have to stop drawing it somewhere. And so we put another line at the very outside, but that's not really a node. Technically, it kind of goes on forever. This is what a 3s looks like. 2 radial, no planars. What does a 3p look like? Well, I still need 2 nodes, 1 planar. So I still have, hey, here's my plane. But that's only 1 node at the moment. I need another, and I can't use another planar because it's a p orbital. But what I could do is have a radius. Each lobe can be cut. Effectively, this looks like, imagine an s orbital, and you put a plane in there. The 2 halves then have to bubble out from it. And so as you squish it better and better, they come back to 0. But this is the result visually of where we get our 3p. It is when I have to have 2 nodes, but only one of them got used to be planar. Quantum numbers are a handy tool to talk about what energy level you are at. The greater your n value, the greater your L value, the greater your energy is going to be. You have more nodes, and more of them are planar. This helps us identify the different energy levels that each orbital represents. Each orbital is just a shape that an electron can take that is stable within the standing wave bounds around the nucleus. There are only so many shapes that fit within those bounds. These shapes fit those descriptions, and we can identify them by knowing the n value, the L value, and eventually the m sub L. The periodic table itself is set up to represent these. The left 2 columns are s orbitals, the right 6 are p orbitals, and the middle is the d orbitals. And we will talk more about the d orbitals in another video.